Hi, everybody. Welcome to our first round of IRIS-HEP Fellowship presentations. We have 6 talks today. First up is Zijun Wang. One of his mentors was Avik. Avik, can you say a few words about Zijun's work before he gets started with his presentation?
Hi, sure. That will be my pleasure. Zijun has been working as an IRIS-HEP fellow for the entire summer, and the work he has done is basically focusing on preservation and dispersion of certain type of digital objects that we call UFO models in accordance with FAIR principles, so that it becomes easy for developers to actually preserve them in a way so that it becomes more visible and easily accessible to the entire community. I'll let Zijun speak about his work for the remaining
Thank you. Zijun, you're up.
Okay. Okay, so hello everyone. I'm Zijun Wang, currently an undergraduate student majoring in engineering physics and applied mathematics from University of Illinois at Urbana-Champaign. Today, I'm going to give a final presentation of my project, FAIR Principles Guided End-to-End Cyberinfrastructure for Preservation of UFO Models. My mentors are Professor Mark Neubauer, Dr. Avgi Roy, and Dr. Marcel Feichert, and this project is partly inspired from FAIR for HERP project. First, let me introduce some background information of UFO models and FAIR principles. UFO model is the abbreviation of Universal Fin Rule Output Model. Such a model is used to store detailed information of beyond standard model theory, such as information of particles and vertices in Feynman diagram, and it can be used by Monte Carlo event generators such as MetaGraph to simulate collider physics in the context of beyond standard model theories. Unlike other models, which store beyond standard model physics information in a collection of text files, require further parsing and interpretation before they can be used by every different event generator. UFO models store different information of the particle model in a generator-independent way into different Python files. Such a storage method allows event generator working directly with UFO models without any modification or further interfacing. Thus, UFO models allow a convenient way to access physics model information on different platforms. Now let's go to some details of UFO model to have a better understanding of its format. There are 4 necessary model-independent files. The init.python file is the basis of a Python module. Every generator gets information of the model by reading the init.python file. The basis of model information files is the object library. It defines classes for other variables in the model. Each class has its own required attributes and functions. In this way, different information of the model is expressed in a more clear and accessible way. Function library redefines functions which will be more practical, such as complex conjugate or real and image part of complex numbers, and defines some functions not included in the complex math library, such as the trigonometric functions. The write-param-card.python file will output a parameter card contains all external parameters defined in the model for event generators like MetaGraph. There are 5 model-dependent files required in all models, and I separated them into 2 categories. The first category contains parameters.python file and particles.python file. Parameters store developer-defined parameters representing particles' mass and width and some other constants. Particles.python file stores information of particles in the UFO model. Here is an example of a beyond standard model theory particle. You can see each particle contains its name and text name, its antiparticle's name and text name, particle data group code of the particle, spin, color, and charge of the particle, and mass and width of the particle using variables from parameters.python, and some other optional attributes. Another important content in the Feynman diagram is the vertex, and the other category contains 4 files providing information of vertices. The vertices.python file defines vertices in the model. Here is an example of a 4-gluon vertex. You can see its Lagrangian form and how it is expressed in UFO model. A vertex variable contains its name, particles containing in this vertex, color tensor of the vertex, Lorentz tensor defining Lorentz.Python, and coupling tensors defining the couplings.Python. The coupling orders.Python file gives information about the order of the coupling tensors, such as quantum electrodynamics, quantum chromodynamics, or dark matter. And the above all are necessary files for UFO models. Like any other digital content, UFO models have software and platform dependencies, require version controlling, and can benefit from a unified way of preserving and distributing these resources. Currently, many UFO models have typically been hosted in the FAIR rules model database, but many of those models are simply hosted as compressed containers without any trackable version controlling. The current storage method for UFO models is lack of findability and accessibility, hard for users to find and utilize UFO models. So we hope to introduce FAIR principles, which stands for findable, accessible, interoperable, and reusable principles for UFO model preservation. FAIR principles provide guidelines for long-term preservation of data and digital objects. The guidelines focus on improving the ability of machines to automatically search and use data, and aims to help users better access and reuse those existing data to get new or reproduce old results. In this project, we hope to develop FAIR-inspired guidelines for UFO preservation. We aim to create a set of tools guided by the FAIR principles as a bridge among developers and users of UFO models. For developers, a central public repository will be built to handle registration and verification of UFO models. Developers will be able to conveniently register their UFO model. Each model will be identified with a set of keywords, including the archive identifier or the digital object identifier for the associated publication. A continuous integration tool available via GitHub will perform automated checks on the file being committed and will provide feedback to the developers when necessary. As a result, the work done by the theorists and phenomenologists will receive better visibility within the community, and they will be able to document and revise their models better. For users, a Python-based program will be built for them to search for UFO models using keywords. The program will search the Git repository and offer the users with a choice of potential matches that the users can choose from, and eventually download the models and use them. In this way, users can find existing models more conveniently and quickly to meet the needs of research. Until now, 2 repositories have been built for the project. The UFO Manager repository stores Python programs for uploading and downloading UFO models. Model developers can register their models developed in both Python 2 and 3 environments. Model users can search and download UFO models in Python 3 environment. The UFO metadata repository is used for preservation of UFO model metadata files. When new pull request is made, a continuous integration check will be run by the GitHub workflow to check if the new added metadata file is in the right format. To use the upload function, developers need to prepare a folder containing a compressed folder storing their model files and a metadata.json file containing basic information of the model. You can see the example down here. The metadata.json files need to contain model's author name, description of the model, the archive or DOI associated within the model's paper. The remaining 2 input will be explained later. For convenience, developers can register multiple models in one execution. They will be asked to input the text file containing paths to their models. Developers will have 5 choices when using the upload function. The 2 basic functions are validation check and generate metadata. The validation check will check model files and metadata file. Let's see the example of validation check to better understand what it does. The upload program will first check whether the model folder contains only 2 files mentioned in the file preparation part. Then it will check the metadata file to see whether all necessary information is provided and is in the right form. After that, the upload function will test whether the model can be imported as a complete Python package. Then the existence of necessary model files mentioned earlier will be checked. After that, the program will investigate model-dependent files to see whether those files can work successfully and get information of the model, such as particles defined in the model, number of parameters, vertices, coupling orders, coupling tensors, and Lorentz tensors defined in the model. The generate metadata function will generate a new enriched metadata based on the metadata provided by developers and the model-related information from validation check. Here is an example of metadata file created by the upload program. The first three, the author, paper ID, and description, are provided by the developers. Model name, model DOI, and model version are input in generator metadata part, and the remainings are model-related information from validation check part. The other three functions are based on the previous two and share the same logic. After files are checked and the new metadata are created, the upload program can use the Nodal API to upload and publish the model to the Nodal. A persistent DOI will be generated and will be recorded in the new metadata file. After that, a copy of UFO metadata repository will be forked. New generated metadata files will be added, and a pull request will be created, waiting for continuous integration checks in GitHub workflow. Developers can use upload model function to register their model in the Nodal from the very beginning. If developers have already registered their models in the Nodal, they can create a new version of their model by providing their existing model DOI in metadata.json file. Or they can simply create new metadata files and upload them to UFO metadata for preservation by providing their model DOI in metadata.json file. Before new created metadata can be merged to UFO metadata repository, the continuous integration check will be run. Here is a screenshot of the GitHub workflow. There are three basic checks to maintain all existing files in the repository. The last one is to check detailed information in uploaded metadata file. First, each key in metadata and its corresponding value format will be checked. After that, the continuous integration will compare the current metadata with other existing metadata to make sure that the metadata and its model has not been registered. This step is achieved by checking model-related information, model version, and paper ID. At last, the continuous integration will check whether the DOI page can be accessed. This step contains a 5 minutes waiting time to make sure the just generating the Nodal DOI works. Then let's go to the download part. The download.python will connect to the UFO metadata repository to access all your model metadata files and allow users to search for and download models. Users can search for models based on models paper ID, models DOI, and PDG codes and names of particles they need in the model. Here is an example of searching for models. We first choose to search for models based on model DOI. All related models, such as models with input DOI and its other versions, will be found. The feedback of search is given in the form of a table containing all possible models, presenting the metadata file name, model's paper ID, and description of the model. Users can continue their search as many as possible. Then we choose to search based on PDG code. Users can input multiple PDG codes of particles at the same time and get the same format of feedback. Users can also download UFO models. Here is an example of using download model function. The metadata file list will be provided, and then users can choose files they want to download. Then the program can download model files from the Nodal. You can see that in this example, 2 models are successfully downloaded in a new created folder. Details of how to use upload and download functions are written in the README part of UFO Manager repository. So in conclusion, this project develops a set of tools for UFO model developers to register, preserve, and update their UFO models, and for UFO model users to get access to UFO models more conveniently and quickly. FAIR-inspired guidelines for UFO model preservation are achieved by registering models in the nodal, getting persistent DOIs, and creating and preserving enriched metadata of UFO models. We got explicit permission from Professor Benjamin Fuchs and have uploaded some models to the nodal. Here is an example of the nodal page of the model. And notice that the model currently has 3 versions registered. Paper for this project is in progress to deliver these tools as a community resource, and we will also email theorists and phenomenologists who may be interested in this project. Further modifications on future versions will be made based on community feedback. We hope this project will greatly help the preservation and utilization of UFO models and improve the study of beyond system model physics. And here is the reference page. And that's all. Thank you for listening. Any questions?
Thank you, Zijun. It was a good talk. Any questions for Zijun? Okay, I will ask a standard question. What's something that that you learned this summer that you think is interesting or important, or something you didn't know before? Do you have an example?
Actually, I think I learned a lot for the summer. The first is the basic properties of the particle physics, like how the Feynman diagram works, what it can show us about the what information the Feynman diagram shows to me. And the second is the Python programming skills. Like originally I only took a basic Python class in college, but during this project I learned a lot of advanced skills of Python by myself and from my mentors.
Great,
So
thank you. Dan, you have a question?
Yeah, I was wondering to what extent this is extensible to new parameters for the models.
Sorry, I'm not quite understand the question. Sorry.
Well, you've got a set of parameters that you use to define the model in the bibliographic data. And to what extent is it extensible to add new parameters as people develop new models? Or am I not making any sense?
I think I can help out Dijun a little bit here. So basically, as long as people develop the models using the predefined format of the UFO model, I think all parameters will be captured by these tools and stored in the metadata. And because this entire project has been developed based on how the UFO models are formatted and stored, so if that basic format is changed, probably we'll have to make some modifications to include additional kind of information that might be available in a different format.
Oksana, you were one of Durbar's mentors. You want to say a few words before we get started?
Yeah. So it was a fun summer together. So basically the project was really kind of complex in the terms of it's not only about the software package, but it's about more like facility, whole system together. So that's why Durbar, I think he managed to go through all the layers, all the technologies one by one. And I think results are pretty encouraging. So we will definitely continue working on this topic. And I really wish Durbar, I hope you will enjoy your future work in university. And as well, please, you're always welcome. If you want to contribute back to this project, you're always welcome.
All right. Thank you, Oksana. Durbar, it's all yours.
Okay, thanks. Yeah, so the project I've been working on for this summer is essentially based on developing various metrics to define the user engagement activities on the coffea-casa analysis facility deployments. And my mentors for this project has been Oksana Shadura and Ken Bloom. So starting off, this is the current existing infrastructure of the entire coffea-casa facility. As you can see that there exists a Jupyter Hub, which is for underlying the entire facility, which is shared between the individual users, which is connected to individual task schedulers, which in turn contains the Jupyter kernel and task workers, which may be connected to the other components of the entire infrastructure. So our objective for this project has been, can be summarized as follows, that Coffee is an existing prototype package for pulling together all the typical needs of high energy collider physics, experiment analysis using the scientific Python ecosystem. It is a high energy physics community project collaborating with IRIS-HEP. So our project defines certain various useful metrics on the facility based on the data collected across various platforms which form a part of the underlying infrastructure, including Jupyter Hub, Dask, and Kubernetes clusters, among others, which, as we saw in the previous slide, are essential components of the existing infrastructure. And based on these metrics, we may monitor the analysis facility efficiently and get an idea of the user engagement of the coffea-casa analysis facility. Some of the metrics that we have ventured into are system metrics, while others give us a more deeper insight into the activity of the individual users. We have also defined a package known as AF metrics, which will automate this entire process of monitoring and data collection process for this entire telemetry process here. So we have used the following tools for this project. We have used Prometheus monitoring tool to monitor the various metrics that we have defined on the Jupyter Hub and Dask servers in the infrastructure. The Prometheus server runs at certain specified ports on the device, and the user can visualize the list of active target levels from the Prometheus dashboard, from where the metrics are being scraped via Prometheus. And once the Prometheus server is running, we can connect it to Grafana for generating easy to visualize dashboards using the script metrics. Now, these dashboards that are generated using Grafana tool, they give us a clear understanding of the various metrics and how they may help us get an idea of user engagement on the coffea-casa analysis facility. So this is the typical Prometheus infrastructure. And as you can see, the architecture of Prometheus is actually pretty complex. Since there are multiple for establishing the endpoints and connecting it to a particular server, we can use various means. We may use Kubernetes on cloud. We may use it locally as well. And based on which mode we approach, there again may be certain typical procedures that we need to follow, for instance, using alert managers. And as you can see, typically Prometheus is used in collaboration with Grafana, which is more convenient tool for visualization purposes. And for this project, we are using a very similar way of the target discovery for services via Prometheus. Now, the possibilities for monitoring of coffea-casa analysis facility installation include the coffea-casa specific endpoints, which is supposed to be able to monitor coffea-casa analysis performance. And this Dask.distributed exposes the scheduler and worker at the matrix endpoint of the particular path. The Jupyter Hub metrics endpoint also exposes the various metrics which may be individual as well as over the entire facility for the particular Jupyter Hub platform. And the Kubernetes specific endpoints are also available, which can be directly accessed via Prometheus. Now, as we saw in the previous slide, we have discussed the existing infrastructure. Now we are proposing certain changes to the existing infrastructure, which include we are proposing that there should be a Jupyter Hub endpoint, which will be one for one of the Jupyter Hub endpoints will be for all users. There will be a task scheduler endpoints, and each these endpoints will be one for each individual user. And there will be a coffea-casa endpoint, which will be one per user, and it will be available via the AF matrix module, which we have defined ourselves. And in future, this project can have multiple useful additions based on the needs and the scopes as well. We can add multiple other endpoints for other services which form parts of the infrastructure, such as Service X, Xcache, or HD Condor. Now, as we have mentioned, there have been various types of metrics that we have looked into. We have categorized them as system metrics as well as application-specific metrics, which give us a broad overview of the individual users' for engagement activities. We can also summarize them as follows. The metrics may be resource utilization metrics for Kubernetes, Jupyter Hub, task scheduler, as well as workers. The metrics may also be performance metrics, which an instance of which is which will be giving is how fast the user can run analysis. The metrics can also be community engagement metrics based on multiple individual users which form part of an entire community. And based on the necessity and the requirements of this entire project, we may also be including multiple other such metrics, custom metrics in future. So we are always open to suggestions, and they can, like I said, that this is still an open project, and we have just shown that it is possible to monitor the entire analysis facility via a certain means, and by this procedure we may also extend it in future based on the requirements of the project. And some of the metrics that we have scraped for Jupyter Hub are Jupyter Hub total users, which will be giving us the total number of users on the facility. Jupyter Hub running servers, which is giving us the number of user servers that are currently running in the facility. Jupyter Hub request duration seconds, which are essentially which is returning the request duration for all HTTP requests across the service. And for task, some of the metrics that we have looked into are task workers, which may be either idle or active, or they may be dead as well. These metrics may also be giving us the total task scheduler tasks. They may be returning suspicious tasks, waiting tasks, error tasks, and tasks which are presently in memory. So now let us explain some of the results that we have got while looking into these various metrics that we have listed below. So the first one, as we have mentioned in the previous slide, for Jupyter Hub is Jupyter Hub total users, which is essentially giving us the total number of users across the facility. In the first plot, it is returning us the total number of users over time after coffea-casa has been migrated to the new hardware. So currently there are 20 total users in the facility, and the second plot is giving us the total number of active users who are currently using this facility. So as we can see, we may also modify the time, the duration of time or the period over which we want to look into the number of users who are using the facility. So the plot is time dependent, and this entire time frame or the time window can be varied as per our needs. Moving on, this is yet another matrix which is returning the request time for HTTP requests with Jupyter Hub auth authorized handler, and it could be enabled for any type of handler, including custom handler as well. So the matrix is Jupyter Hub request duration seconds bucket, and as we can see, depending on the types of handlers, there have been multiple plots over time. And same goes for this particular matrix as well. We may vary the time depending on the period within which we'll want to look into. Moving on. This is essentially a screenshot of the endpoints that collect data for all the plots, which we'll be seeing now onwards. For this is we have looked into this in the we have mentioned this in the previous slide as well. This is essentially the result that we'll be getting after connecting Prometheus to the analysis facility server that is currently running. And we once we have connected, once the connection is established, then we may look into the matrix endpoint, and that will be returning us these results. So we have also connected Prometheus to the analysis facility server, and once the connection has been properly established, we have connected Prometheus to Grafana dashboard visualizer, which is and we have also configured the Grafana dashboard for each individual user using the facility. And there have been two dashboards that we have generated for each user. One is based on the Jupyter Hub of that particular user, and the other is based on the task scheduler and workers for that particular user. So here the dashboards are generated for per user, and as well as we may also be generating dashboard for the entire facility on coffea-casa. Moving on. So this is yet now we are looking into the various task metrics that we have looked into over the course of this project. So this is essentially task scheduler workers, which will be returning the number of workers per user over the course of time. This helps us to monitor both idle as well as saturated task workers in Kubernetes and HD counter. So as you can see, there have been multiple graphs generated in that plot. One of them is, there have been 3 graphs, in fact. One of them is returning us whether the state is connected, the state may be ideal, or the state may be saturated. And depending on the time frame, the graph may vary, as we have mentioned previously. Moving on, we have now in this particular matrix, we are using task scheduler task, and we have specified the state to be processing. So what this does is that it will essentially help us to monitor progress with processing tasks on scheduler. And it is available for each individual user on the coffea-casa facility. So for this particular screenshot, we have analyzed the dashboard for Alexander Held, who was the user whom we have been monitoring over the course of time. So as you can see from the plot also, the time window you have selected is for a period of 2 minutes. So depending on necessity, we may change this and the graph will vary accordingly. This dashboard is essentially generated for Oksana Shadura. It is pretty much the same as the previous one. The state here is processing, and as you can see, the job is for Oksana's task server, and will help us to monitor the progress with processing tasks on scheduler. And there isn't any stuck workload, as you can see. And again, the particular time frame for this specific matrix that we have monitored is 15 minutes. We have selected, and it can vary. Now we have changed the state of that particular matrix to erred, which will help us to monitor the tasks that were errored, and this will significantly improve the debugging procedure. And for this particular example, we have again monitored Oksana Sadura's task server, and as you can see, this is the result we have got. Moving on. So here we have changed the state to memory. This helps us monitor the tasks that were in memory, which will again significantly improve debugging if, for instance, we were running out of memory on workers. To explain it a bit in more details, task.distributed stores the various results of tasks in the distributed memory of the worker nodes, and the central scheduler tracks all data on the cluster and also determines when data should be freed. The completed results are usually cleared from memory as quickly as possible in order to make room for further computation. So as you can see in this particular slide, we have included the plots for both Alexander Hill's task server monitoring results as well as that of Oksana's. Moving on, here we have again modified the state of that particular matrix to waiting, which is essentially helping us monitor the tasks that were in waiting state or that were waiting in queue, which again will improve significantly the debugging procedure, and it may also help us detect deadlocks. So this is again the plot has been generated for Oksana Shadura. Moving on. So this is a different matrix that may be pretty useful for us. This is generated for Oksana again. So task scheduler tasks suspicious total. It helps us monitor the total number of times a task has been marked as suspicious. The number of times a task has been involved in a worker's death is basically what is returned by this particular matrix. Some other tasks may cause workers to die, such as calling OS.exit 0. And when a particular worker dies, all of the tasks on that specific worker are reassigned to others. This combination of behaviors can cause a bad task to catastrophically or potentially destroy all the workers on the cluster one after another. So whenever a worker dies, we mark each task currently processing on the worker as suspicious. So as you can see, over a course of 2 hours, Oksana's task server has returned the task suspicious for 90 times. And depending on the time frame, this plot may again vary, as we have mentioned before. Again, this is another useful matrix that may be generated per user. For this particular example, we have generated a plot for Alex Health. And this terminal currently running total is essentially giving us the number of terminals running for in that particular task server. So as you can see, the plot is returning the number of terminals ran by Alex Health over a course of 30 minutes. So yeah, this graph gives us an idea that our users on the coffea-casa analysis facility are indeed using terminals. Yet another matrix that I've looked into is task scheduler task forgotten total, which is used when the task is no longer needed by any client or dependent task. So it just disappears from the scheduler as well. As soon as a task reaches this particular state, it is immediately dereferenced from the scheduler. And this plot has been generated for Oksana again, and it has been generated for a course of 30 minutes. Yet another matrix that I've looked into is kernel currently running total, which will basically return us the number of different kernels that are being used by our particular user. And for this particular graph that we have used in the screenshot, we have specified the type to be Python 3. We may also change it to certain other types of particular kernels that we wish to check whether the particular user or the system is using. And so as you can see from the graph, it's pretty evident that Python 3 and multiple other notebooks are running in parallel. And if we don't specify Python 3, it will just return us the various types of all the types of kernels that are currently running for that particular server. Moving on, this is the Prometheus matrix that we will be receiving for that we have received once we have connected Prometheus to our custom AF matrix Python package that we have defined over the course of this project. And we from this particular result, we have tried to investigate if we can use or develop our own handlers to collect custom information. We are interested to collect custom metrics for analysis facilities such as efficiency of analysis. And as you can see from the at the bottom of the the result that we have received, we are getting results for various based on the various output of that particular notebook that was being run and that was being monitored by this package. And the package was essentially connected to this specific notebook, and the Prometheus server was in turn connected to the results of this that was being returned by upon running this particular package. And again, that Prometheus server, once it is connected to the results of the package, we may again connect Prometheus to Grafana, which will essentially help us generate the dashboard for convenience. And as we can see here, the outputs included bytes read, a specific value based on the result returned by that specific notebook. Bytes read, entries, process time, and chunks were the various results that were being returned by the upon running the notebook. And based on the like you said, based on the result returned up by connecting Prometheus to that particular notebook via our AF metrics package, which we have defined ourselves, we may also further connect Prometheus server to Grafana, which will help us generate convenient dashboards. So this is what we have done in this particular slide, and we are essentially just investigating if we can develop our own handlers, like you said in the previous slide. And this is the difference, is that now we are connecting it to Grafana for better visualization. As you can see, multiple multiple graphs have been generated in the single plot here, because of there have been, as we saw in the previous slide, multiple outputs were being returned upon running that single notebook, including bytes rate, chunk size, process time, chunks, as well as entries. So based on the values of those specific parameters, we have got different graphs over the course of them. So like I previously said, we have just laid the foundation for this entire monitoring system on the of user engagement metrics on the coffea-casa facility by means of our project. And we have also established that such a venture is very much realistic and possible. But just like we have shown, there are scopes for improvements, as we have mentioned in the previous slides as well, that for instance, the entire monitoring system can be extended to other components of the existing infrastructure like HD Condor, Xcache, etc. So there are provisions for improvement as well, and I'd love to collaborate further and if in future if possible, and extend improve the results of the project. So the various scopes for improvement of this project, which make up for our future plans, include deploying and testing all achieved results on the open data as well as CMS coffea-casa analysis facilities, investigating more complex analysis facility metrics in addition to the ones we have already mentioned, and certain other ones that we have looked into during this project, and also addition of custom request handlers to serve efficiently specific analysis facility metrics. You can learn more about this from this particular documentation provided by Jupyter Notebook. So yeah, that's all from my side. Now I'll be taking questions from you guys. Thanks.
Thank you, Durbar. Any questions? Avik?
Hi, Durbar. This is a nice presentation. Thank you. I just wanted to ask, like, do you see any potential application of these metrics in that you can use them in real time for resource management for this entire facility system?
Yeah, am I audible?
Yeah, we hear you.
Yeah. So like I said, there are provisions for including more useful metrics in future, as well as what we can do, and we have done as well, is that we may define our very own custom metrics, and we can define what that particular metrics will be returning. So for resource management, essentially we may define certain specific system metrics which will be useful for us. And depending on the particular application and or the particular particular parameters that we wish to look into, that's very much possible in future. I hope that answers your question.
Yeah, thank you.
I've got a question if there's time, Rob.
Yeah.
Yeah, go ahead. Court.
Perfect. So this how is it that the notebook that's receiving the data and hopefully it will you know, with these handlers that you're talking about here displaying the data, how does it know to get the proper, you know, how does it handshake with the server so that it gets its notebook's performance data as opposed to, you know, user X who's sitting next to you?
Could you please come again? I didn't quite get your question.
Sure. The data that is being generated by these plugins is kind of come from every notebook that's running in the system, right?
Yeah.
So when you're displaying it in your user's notebook, you have to have some way of selecting out only the data that's relevant for that user's notebook, right? And I was just curious how that handshake was going to occur.
Yeah. So maybe I can reply. So basically, yeah, we have this handle per each user. So this already kind of like separating them. And then we can also get, so we were thinking about this because it's really like if you try to collect continuously, for example, for Alex, we tried and he's running many different notebooks. So we can try to generate basically some particular unique name like string for the let's say to define the analysis. For example, it could be, since we are focused on the coffee, it could be just the name of the coffee processor, the class that we are using, and then probably adding some unique like. So basically, this is still under investigation. It's something that I'm interested to continue.
Okay. Perfect. Thank you.
Great. So Benjamin, one of your mentors was Simone. Simone, you want to say something about Benjamin's work?
Yeah, I'll be happy. Yes. So Ben has been working with myself, Sergo, but especially with Carol, who's actually just finishes a postdoc at LBL, Status Faculty of Birmingham. And so Ben has been working together with another student as well, Natalie, who will be giving a talk in a week from now on reconstruction algorithms for a muon collider detector. So this is a very nice project in the sense that allows the students to really see a detector coming up from the basics. And Ben has been, I personally have to say, has been a pleasure to work with Ben on this project. It's I have to say I've been impressed by the amount of progress you've been doing, Ben. So it's I hope people will enjoy this presentation. There is a lot of good work in it.
Thank you very much, Simone. Okay.
Thank you. Go ahead, Ben.
Thank you. Okay, so for my project, I worked on reconstruction algorithms dealing with electrons. And my three mentors were, as Simone mentioned, Carol, Simone, and Sergo. So there have been a few proposals for a new collider. One of those is a muon collider. And as a lot of colliders these days use either protons or electrons. For example, Delaware uses protons. But in comparison to protons, muons are fundamental particles, which lets all the energy of a particle be used in the collision, and the initial momentum of the particle is also known, which is very helpful when doing calculations. Also, compared to electrons, which are used in a number of other accelerators, muons have a much larger mass, so less energy is lost when they are accelerated. As for the efficiency, you can see where these two lines meet, and on the x-axis, you can see that approximately 14 teraelectron volts in a muon collider. So the x-axis is the muon collider, and the y-axis is what the LHC is. Around 14 teraelectron volts is equivalent to around 100 teraelectron volts at the LHC. So the muon collider is a lot more energy efficient. Not all is peachy though, and there are a few problems with the muon collider. First of all, is that muons are harder to collimate than the previously mentioned particles, and that they also decay inside the particle accelerator, which causes beam-induced background. As you can see by this middle and left graph, the decays from muons do light up the calorimeters and other detectors, making it hard to track particles. Special relativity allows muons to actually accelerate to the necessary speeds. And out of all the decays of the muons, the one that I've been looking at the most is electrons. As for the goal of the project, it is to study electron reconstruction algorithms and to identify necessary improvements. And just a bit of background, particle identification is done by analyzing tracks created in the inner detector through chains of hits, and also by measuring the energy deposition and depth into the calorimeters. As you can see in this bottom left-hand graphic, this yellow electron leaves a track in this inner gray detector, and then should have a full shower in the electromagnetic calorimeter and should not reach the hadronic calorimeter. The photon, which I'll bring up later, is similar, but it does not leave a track in the inner detector. On this right-hand side, you can see how a particle could curve, how a charged particle could curve due to the electric field inside of the detector. And given the curvature, we were able to determine the momentum as well. So the ugly truth about electrons is that there are some problems with tracking them. For example, they undergo Bremsstrahlung and multiple scattering, which makes them difficult to track. In this graphic here, you can see how an electron in the presence of a nucleus will curve around it and emit a photon. This is an exaggerated curve. It would not be this extreme, but you can see how through chains of Bremsstrahlungs, that the curvature of the particle could greatly change, and it can make it difficult to track. So for the particle data that I was working with, I did some simulations and then did reconstructions on those simulated particles. But what it did was I have a sample size of 10,000 particles with no beam-induced background, which is important to note. And the transverse momentum of the particles is from 1 to 1500 gigaelectron volts, a polar angle from 10 to 170 degrees, and an azimuth essentially around the entire detector. I'll be using conformal tracking, and the particle identification will be done by Pandora for everything here, unless otherwise specified. Two things I want to point out are that the transverse momentum has pretty high efficiency, but at higher transverse momentum numbers, it does fall off a fair bit. As for the polar angle, it has a very, very high reconstruction efficiency, except for the forward regions of the detector near 0 and 1 pi radians, where the efficiency drops dramatically. And this is the only time we're going to be seeing an azimuth graph because the data is essentially just standard all around. There really is not much change in one region as opposed to another one. As for the types of reconstructed particles, I should really only see photons, which is the result of Bremsstrahlung, and electrons. it is possible that photons could be misidentified or could be due to like some fake tracks, but really you should just see photons and electrons, which means that all of the neutrons and neutrons and pions, which are in green and black, are incorrectly reconstructed. If you look at this bottom right-hand graph, something I want to point out is how there are some peaks, like in the near the forward region, a bit in from it in the detector at around 0.5 radians. And this is true for both the pions and for the photons, which is something I am going to talk about later. As for the particle matching methods, the particle linking, so when after a sample of particles is reconstructed, linker goes in and puts weights between the reconstructed and truth particles, depending on the number of track and calorimeter hits and energies between the reconstructed and truth particles. And from I created 3 matching methods. The first one is simple electron matching, which is where the reconstructed electron with the highest weight is treated as the truth particle. Best match method, which is where the particle with the highest weight out of the reconstructed electrons is selected. And if no electrons were reconstructed, it then searches through all the photons to find the one with the highest weight there. As for the sum matching, it takes the sum with the momentum for all the electrons and photons and just treats the result as a regular particle. And this tries to account for any Bremsstrahlung that happens and tries to reconstruct the parent particle. For example, here you can see how there could be a change in momentum due to this original electron down here emitting this photon and sending the electron off to the side. As for the transverse momentum between the simple electron matching and for the best match method, you can see how the best match method in red, it has improves a lot upon the transverse momentum in efficiency in the high transverse momentum region. And as for the polar angle, it also jumps up a lot in the forward region. And this gap in the high transverse momentum region is likely due to either like Bremsstrahlung occurring less frequently, which means that the track may not exhibit traditional electron behavior, or because the punch through was higher in the electromagnetic calorimeter, which means that there could be a deposit in the hadronic calorimeter, which is uncharacteristic of photons and electrons and will confuse the identification algorithm. For the resolution of the matching methods, which is just the truth transverse momentum minus the reconstructed transverse momentum of the particles, for both the simple electron matching in blue and for the best match method in black, you can see that there is a high tail on the right and essentially nothing on the left. This means that the truth transverse momentum is generally higher than the reconstructed transverse momentum, which does hint that something is missing from the reconstructed transverse momentum. The sum method tries to rectify that by adding in all of the potential Bremsstrahlung photons and does achieve a nice Gaussian distribution around 0, which is good to see. And it does give a nice data set that can be worked with. As for the track data of photons, and just for photons in general, you can see how the transverse momentum in this bottom left-hand graph does steadily climb, which is like the inverse of what was seen in other efficiency photon of electron reconstruction graphs. And this does make sense as particles with high transverse momentums or just high momentums in general are more likely to punch through. Because if a particle is to say a high transverse momentum and a polar angle on the extremes, it means that the particle could have a much greater total energy, perhaps in the 5,000 gigaelectron volt range. Photons are the particle that electrons are most commonly misidentified as. And for the tracks, which should only be created for electrons, you can see that out of the 551 photons that were linked, 541 of those particles are tracks, which means that most of the photons did actually have a track and were just misidentified. Also, an interesting thing of note is that the polar angle of the photons is also on the extremes, which would make sense given that it means that those particles are more likely to have larger total energies. If I then do a sanity check and check with the visuals in the simulation, I can see how the particles do have a extreme polar angle, and these are just the first two misidentified electrons that I came across in my simulation, and they're both photons, and this is what they were like. And you can see that for both of them, they punched through the green electromagnetic calorimeter, which is where electrons are supposed to stop, and it continues into the hadronic calorimeter, leading to misidentification. As for pion occurrences, pions are most commonly restricted at higher energies as well, similar to photons. You can see a similar upward slope, similar to the photons. But the biggest change between photons and pions is that there are two mountains in the pion region, but they are not exactly at the very edge of the forward region. And in fact, they are a bit in, so around 0.5 radians. And this just happens to be where the electromagnetic barrel and end cap overlap, which means that in the transition region, the pattern recognition is failing. As for the once again, if I do a sanity check, I can see how in this bottom middle graph, I'm not sure this is super visible, but there is a green line that goes through this more swamp green electromagnetic calorimeter barrel and this lime green electromagnetic calorimeter end cap. It is also possible for pions to be reconstructed if a particle once again has high transverse momentum and or just high momentum in general and just punctures through the electromagnetic calorimeter and goes into the hadronic calorimeter. If I would do some math here to estimate the shower depth, if a particle was to have the maximum 1500 gigaelectron volts, the shower depth would be around 15.3 centimeters. And in the simulation, the electromagnetic calorimeter is only 20 centimeters thick. So statistically, it would make sense that that some particles do make it to the hadronic calorimeter. If I compare the conformal tracking versus the axe tracking, which is which is hopefully the new standard, there are some changes, and just want to cover how axe works first. What it does is it finds essentially every combination of 2 to 3 hits in the first few inner detectors, and using that, it propagates a track along the detector, and if it runs to a particle, it adds it to the track and adjusts the trajectory accordingly. And compared to conformal tracking, axe does have significantly worse reconstruction efficiency. For example, you can see in this solid blue, which is the axe tracking, it is significantly below the conformal tracking for simple electron matching as well. The best match method also changes a bit, but not nearly as much as the simple electron matching does. ACTS also finds significantly more photons, but also less electrons and pions, as shown that the solid green line and solid blue line are below the dotted lines. If I then go in and change some parameters for ACTS, for example, changing the chi-squared cutoff from 10 to 15, which broadens the selection fits per layer, and if I also increase the number of measurements from 1 to 2, which means that it follows 2 separate seeds per layer, I do see some good changes. For example, it essentially fixes the problem with the efficiency fall off at the high transverse momentum region for simple electron matching. As you can see in the dotted blue, which is the new parameters, it is essentially straight across, as opposed to how the original parameters dip. And the fact that like the best match method matching efficiency stays essentially the same, while the electron matching goes up, it does mean that there were a lot of photons that were reconstructed as electrons, or a lot of electrons that are reconstructed as photons, which are now reconstructed as electrons. So for conclusions, the track finding is quite accurate, but identification does need a bit of work. Electrons are most likely to be misidentified as photons, and then second most likely to be misidentified as pions. Particle identification also needs some help with high energy particles that enter the hadronic calorimeter, and also particles with energy depositions in the transition region. ACTS does help with dealing with electrons at the high end of energies, but it does decrease efficiency. So the identification of, although one of the upsides is that the identification of photons and pions is less tied to the polar angle, which is good to see, and hopefully there can be more general solutions that will solve it for both, that will solve misidentification for both pions and photons. But at the end of the day, changing ACTS parameters is about optimizing what data you want, and it does probably take some optimization to get some ideal numbers being put out. So that's why I am recommending that for a potential future project, or for something to work on, is that some parameters in Pandora and ACTS should be optimized by machine learning. And thank you very much. All the code and graphs used here have been uploaded to this GitHub. Any questions?
Thank you, Benjamin. Any questions? Oh, there's a question. Marcus?
Thank you very much for this interesting talk. I have not a question, I have a comment. Your work is not only relevant for the muon collider, it's also very relevant for the electron-ion collider, which we are currently putting together. So we are using ACTS for the electron-ion collider, and the main process is deep inelastic scattering. So the task is to find the scattered electron. So from all the tracks, the main task is to know, oh, is this a lepton or is it a hadron? And I think your work is also relevant there. So so very much for doing that. This was really interesting.
Thank you very much. That's very, very interesting to know.
Any other questions for Benjamin? All right, thank you, Benjamin. Good talk. So Tetiana was mentored by Marcus. Marcus, do you want to say a few words before Tetiana gets started?
Well, thank you very much for putting this fellowship project together. I had not planned to have this summer a student working with me, but I was very pleased at the end that that I said yes to supervising a student. It was a lot of fun to continue this this project, and really on one hand work a little bit with software, but on the other hand, really work in a nuclear physics on a nuclear physics state-of-the-art problem. And this is related to the physics which we are doing at Jefferson Lab, but it's also related to what we will be doing at the Electron Ion Collider and what has been done, and that is what Tetiana will present at previous facilities at DESY in Hamburg, and what is going on the nuclear physics program at CERN. So yeah, it was a lot of fun, and I really applaud you guys for putting up a really impressive fellowship program. That's a lot of work, and for me as a mentor, it has been a lot of fun.
Well, we humbly accept your gratitude. Tetiana, you're up.
Okay. So hello everyone, my name is Tetiana Yushkevych and I am PhD student at Odessa Polytechnical National University. For this summer fellowship, the title of my project was Tools for Understanding Semi-Inclusive Deep Inelastic Scattering Measurements. And let us start with semi-inclusive deep inelastic scattering. So, in semi-inclusive deep inelastic scattering reaction, a high-energy electron scatters off a quark within the nucleon. These quarks form a hadron in the final state, which is detected along with a scattered electron. This you can see in the figure 1. In general, pions in this reaction are produced from the fragmentation of the struck quark, is the current fragmentation region, remnants of the struck nucleon, its target fragmentation region, or from gluons radiated in the process. As you can see in the figure 2, there are several types of these regions. I would like to tell you more about Team Ds because Team D is studied in CDs. Transverse momentum distributions are the distributions of the hadron's quark or gluon momenta that are perpendicular to the momentum transfer between the beam and the hadron. Team Ds provide information on the confined motion of quarks and gluons inside the hadron and complement the information of the hadron's structure provided by Parton distribution functions. So PDFs related to the longitudinal structure. So simply said, Team D is about the imaging of quarks and gluons. I want to give you an idea of what it looks like. So in the upper right picture, you can see the momentum densities as a function of x. X is the momentum of the proton, is momentum fraction of the proton momentum carried by the quark. So as you can see, the density located in the center. This gets interesting when you write momentum distribution in a transversely polarized nucleon. Interesting thing is have been found where either depending of the flavor of the quark, the densities are on different sides. For this fellowship project, we set such goals as to study the paper New Tool for Kinematic Regime Estimation in Semi-Inclusive Deep Inelastic Scattering and the Affinity Tool, to study the influence of non-perturbative parameters of the affinity results and see how reliable these results are in order to guide experiments and phenomenological studies of nucleon structure. That whether there are any dominant parameters that most affect the results, and writing new software using Jupyter notebooks for studies of the parameter space. I want to note that all these goals were achieved. For data analysis, we use the affinity tool. This tool depends not only on quality that can be measured, but also on parameters of the underlying theory that cannot be measured. So this slide provides a brief visual explanation of what an affinity tool is. So the affinity is the percentage of the number of appropriate values that got into the box over all generated values. Affinity is important because it helps you to understand are you in team D or any other region. The box defined by ratios is R0, R1, and R2, which is presented in this table from the article, and also non-perturbative parameters which are used to calculate the affinity tool are presented here. It's delta KT, KIT, KF, KI. The region indicators RI depend on CD's measurements and parameters from non-perturbative QCD that are not well known. So our four non-perturbative parameters are defined as follows. Each of these parameters has a dependence on the three variables. Therefore, we conducted two types of studies. Fixing the value one of the parameter to find out which parameter has the greatest influence on the affinity results, and changing one value of the first variable lower boundary on the output interval for one parameter to confirm or disprove guesses that it is it that affects the affinity results. For my work, I used Jupyter Notebook tested at Jupyter Lab at Jefferson Lab that allows to easily share notebook and results with colleagues. It mainly ran on my laptop, and Python libraries such as NumPy and Pandas to calculate the affinity tool, and Matplotlib to plotting graphs. Using this graph, I want to explain what you will see in the resulting graphs. In inclusive deep-inelastic scattering, everything depends on the X parameters, but if we talk about semi-inclusive, then you have the additional variables such as pH-perp or pH-T and the set of the hadron. All of these variables are relevant, but depending on the paper, we can only show 2 dimensions. So let us look at the leftmost square. All is red, and that means that is absolutely no affinity for these TMDs. Let us focus on this plot. There is a certain X for Q square region is 0.04 in that bin, and the certain Q square 3.7 G square bin. We are now at low X. Depending on the symbols, triangles and round and circles, we look for the various sets. The round data points is the low values of set, and these triangles that goes to the left is high values of set. So you can see that in this plot, the more high values of set, otherwise the lowest, and the lowest values of set otherwise are highest. So each of these panels, 6 panels, represents a certain region of X and Q square. And all of them have the information about pH-T. All of these panels show the density of the affinity. And if the affinity density tends to blue, then we can say that yes, this kinematic region can be described in terms of team D. So for Hermes is the experiment provided on Hadron Electron Right Ring Accelerator, and now it's over. For this experiment, we can only interpret the results for team D at high X region for low values of PhD. So if we fix the delta KT at lower values, the affinity will go up. This means that affinity is more sensitive to this parameter. We did all these graphs for 4 non-perturbative parameters, but delta KT affects a lot on the affinity. And this is not only for the team D region, it's for collinear region too. And not only for the Hermes experiment, we did it for Compass experiment. It's a nuclear experiment provided on LHC, and it's still ongoing. And but in Compass you have a large Q square range, but you have the smaller values of X. And as we see, the affinity go up for the lowest variable of delta KT for team D and for collinear region too. So let us make conclusions for these graphs. So one parameter was found that most affect the results of affinity. This parameter is delta KT, which is good for characterizing an intrinsic relative transverse momentum in the large Q limits. It was also found that indeed only one variable, it's the lower boundary of the output interval, has the strongest influence on the results of plotting. And when examining the graphs for the collinear and team D region, it turned out that in the area where the highest affinity match for the team D region is, the same area will have the smallest match in the collinear region. This means that there is a kind of clear separation of these areas. And for the final, I also would like to say that the fellowship program gave me a lot of opportunities, such as opportunity to work in a team studying semi-inclusive deep and elastic scattering. It was really great experience, and I like to work with all of the members of this team. Also, it gave me opportunity to learn the Python programming language and the advantages of the interactive Jupyter notebooks, because before that I was only familiar with C and Fortran. And I want to point out that IRIS-HEP Python tutorial was really helpful for me with learning the Python programming language. And this program gave me the opportunity to learn more about the Python theory that describes semi-inclusive deep and elastic scattering. So that's all. Thank you for your attention.
Thank you, Tetiana. We're happy to hear those things, and we're glad you got useful things out of the opportunity. All right, any questions for Tetiana?
I just wanted to quickly say that was a great talk, and I love how you were only familiar with C and Fortran, which is something many of us were not even familiar with that. So you were already starting with a leg up, but very nice work.
Thank you.
All right. Thank you, Gordon. Anyone else? Oh, thank you, Tetiana. So Oleksii was mentored by Mario. Mario, want to say a few words before Oleksii gets started?
Yes, thank you. Let me start by saying that this has been an incredibly interesting project because, as you might know, at least those who have been dealing with dataset transfers, this has been a problem we've been trying to tackle for quite some time now, and we had PhD students on this and R&D projects, and there were some results. But now we had the unique opportunity to get a fresh view on this from someone not in the field, which is incredibly valuable, because then this kind of takes the bias out of your analysis. So now when Oleksii said, okay, what can we do during the summer? I said, okay, I have the perfect thing for you. And so basically what you're seeing here, there was no framework, there was no existing software. This was everything built by Oleksii himself in those 2 months during summer. So I'm incredibly proud of the work that was done. Yeah, I don't know, Oleksii, you want to start?
Okay. Hello, everyone. My name is Oleksii, and I am a student of Kharkov Polytechnic Institute. This summer, I was working on the data analysis project to estimate the transfer time of dataset for scientific computing. My mentor is Mario Lasnik from CERN. The research team has done research in this area in the past, including many projects and also a doctoral thesis. The outcome was promising, but needed more independent verification. With the project, I continue the existing research and try to find a new approach and verify the result. The distributed data management environment is very complex, and there is a lot of dynamic interaction between users and data centers. RUSA is the center of everything, and all the data about the transfers and data rules and the life cycles will help to create my model. First, we need to look at the successful file transfer. Here we have the most metadata available. This is based on the RUSA events. This is available in an Elasticsearch instance and can be easily accessed. From this, I generate time series with event metadata like a start date, transfer date, bytes, and many more. There are more than 30 different variables that can be used for this model. In the plot, you can see an example metadata called the activity. As you see, it's very colorful. I decided to use Google Colab because there is nothing complicated to install, and it provides free CPU and enough RAM. It is also possible to continue the project from different devices, which is very helpful. I choose TensorFlow and Keras as a modeling framework because they are the most popular and best supported. And there are some unnecessary columns coming from Elasticsearch, such as type, ID, score, and other. They are unneeded for the analysis, and I removed them and just leave a few interesting metadata from which I could calculate the correlation. And the last 4 columns are originally represented as dates. I converted them to seconds, where the starting point is the minimum value of created times column. And I introduced some metadata as calculated the values transfer duration and queue duration for the existing timestamps. Transfer duration is the file transfer time, which is calculated as the difference between transferred time and started time. And queue duration is the time the file is waiting in the transfer queue, and I calculated as the difference between started time and submitted. Also, on this slide, you can see the correlation table between the values. You can see that the correlation between the file size and transfer time is not very high, and is only 36%. It's good from a statistics point of view, and bad for a model. For the first analysis, I used the random samples of 10,000 records to analyze the data. During the analysis, I examined different samples to check if results were similar across the data I have. In the plot, you can see that scope affect the transmission time. The names of the file transfer contains interesting substring, for example, Monte Carlo data. It's MC, and some number shows the worst result. And let's divide the data frame into subgroups for different scope. And here you can see the correlation plot of bytes and real duration for other scope. The colors correspond to different activity, as mentioned before, and the result is again not quite clear. After checking all the columns, and I saw how much they affect the file transfer time, I came to the conclusion that I need to leave only 7 major columns with data without losing precision. And when you check the correlation between started and transferred, there is something we can do. We divide the file size into categories based on the typically file sizes used in the experiment. We can display this on the dot plot. Interestingly, it's looks as if the file were transferred instantly. I thought that the straight line in the figure was formed due to the fact that most of the data is in the 200, 500 megabytes category, and accordingly, the transfer time is short. I also examined in detail the selected area on the previous slide and came to the conclusion that the display of points looks flexibly. The files are not transferred instantly, but depending on the size and other characteristics. And as a first estimation model, we need a baseline, something simply to understand to compare. The first input was the number and size of files, and the output was the duration in seconds. A linear regression model was the first choice, so we can answer. If we have some data set, identification and volume, when will the data set finish transferring? From the plot, you can see that the data is linearly independent. Just to show how far off it is, I plotted linear regression, so you can see that we need something much smarter. Typical comments from users to the Russia team was always just take the file size and network speed, then you will see how long it takes. This is unfortunately not the case. And so we built a neural network based on 2 input layers: densification with ReLU, and then concatenate densify with ReLU gain. We can take the numerical data, its column bytes, and the categorical data, another column. So we create two branches for these different data and then merge them. We tried a few model structure, and this model structure shows the best result in the prediction value. Changing the number of neurons and hidden layers has almost no effect on the result. I change them depending on the sample size. In general, the structure of the model looks like this, and only the number of neurons changes. On the slide, you can see the result of the model prediction. The MSC metric is quite large, and the target of the is of no, and the target is of course to decrease the error. Also, R2 score is quite high. On the plot, you can see the difference of the training data from the validation and test data. It was decided to take MSE as a main metric since it is easy to interpret and since it has the same units as the original value. It also operates with small absolute value, which can be useful for computing on the computer. And also on the next slides, you can see the normalized MSE, which will allow you to compare the result to different samples. And a very useful way to express model error is to plot the histogram of the error and hope for something like this. Prediction error is in seconds on the lower axis. Most of the errors are closer to zero, but there are small number of outliers. The closer the value is to zero, the smaller the prediction error. This is a nice way to visualize prediction result for a large amount of data. And since of the ninth slide, we saw that the files are transferred as a groups. I tried to simulate this and group it. I tried to simulate this and grouped the file into 10 files. Before grouping the data, I decided to remove the groups with less than 10 records. They are a good result. The loss plot for training and validation data is almost equal, and the values on the scatter plots are located both close to the diagonal. This means the prediction error is insignificant. Next slide. Then I increased the model on a large data set, the maximum I could load in Google Colab. In the real world, it's this about 8 hours of data traffic. The normalized MSE metric is about 2%. This means the average prediction accuracy is almost 98%, which is already very good. When we check the result for the grouped files, I made groups of 10 files, trained the model again, and checked the prediction result. Even with the large input, the model can train quickly, so it can be done multiple times per day. From the result, it can be concluded that the value are predicted quite well, given the fact that the behavior of the Russian is quite complex. A large number of points are inside the diagonal, which means that the transmission time is prediction-like. There will be future work on this by the Russia team. They told me that they will build a component for Russia to integrate the code that they have written. So what that Russia users can know how long it will take for their dataset to transfer. And for summary, I really enjoyed practicing in this project. I gained a lot of knowledge, gained experience with the real challenge. This is very important event in my life. I realized that most of the time I spent on understanding and analyzing data. I want to continue to develop my skills in this direction. And thanks for listening.
Thank you, Oleksii. Any questions for Oleksii? Okay, I have one then. Like I asked before, what was something that I guess stood out to you as far as your experience, as far as something you learned or something you found interesting? Can you give an example of something?
Can you repeat, please?
Yeah, can you like just give an example of something you found interesting during, or something new you learned, or something?
I know that Russia, I don't know, block of the Russia is too large. It's like 25 gigabytes. It's too large data sets. I need to I don't know, cut the files and
so basically the scale was impressive, I guess, or
and it I don't know, always all of this work it's new for me.
Okay, no, that's fine. So Dan, you have a question?
Yeah, the transfer times aren't static. They change with conditions on the networks, conditions at the endpoints. Can this model be dynamically updated to account for those changes?
I don't know. Maybe you rephrase question.
It's basically whether, as new information comes in about the transfer conditions, can those be incorporated in this model in a natural way?
I'm sorry, I don't understand.
Maybe I can explain. So the model that was built right now works on a history of events. And if you want to predict, you will have to come up with a sensible history of events, right? So if you feed the model with events from 3 weeks ago, it might not be useful anymore. However, the model can be trained in, what did we have, 10, 15 minutes? So you could potentially update it 3, 4, 5 times a day and get useful results. However, there is one more thing, and this is something that came out of another work that we had in this area. And this was based on LSTM models, which are incredibly well suited to do time series forecasting. And the idea would be to kind of come up with a hybrid in the near future, so that you can do let's call it continuous learning on the same model as the data comes in. And this is what we're targeting. But right now, it's basically a I go, you go model. Does it answer the question halfway?
Yeah, that did answer the question. That you could retrain periodically and you have other work.
Yes, but right now we would need to retrain the full thing every time, which is obviously not optimal, but yeah, that's where we are.
Yeah, that definitely answered.
Thank you for jumping in there, Mario. Thank you, Oleksii, for the talk. Maxym was mentored by Katerina. Katerina, you want to say a few words before Maxym begins?
Sure. So it's Katerina here, and I'm very happy to have worked with Maxym on this topic. It's something that we've been playing with for quite a while. There was another fellow on compression, not this kind of compression, but it's an interesting topic because we have a lot of data, and if we can compress it to a reasonable level of precision, of course we'll have to give something up. Then we're happier because we can record more data. And this is a test of using both machine learning and also something that Maxym came up with an idea that is principal component analysis. So in principle, they are the concept behind the machine learning algorithm that is using in PCA is similar. You want to compress the information to a set of numbers to another representation, and which one performs better? This is an interesting question that we hadn't asked before, and this has been actually the main part of the project rather than the implementation onto the ESCAPE virtual research environment. But Maxym has been able to do both, which was impressive. And so we have some new results and also an implementation in what is hopefully going to be a working prototype for a European cloud for doing scientific analysis. So I'll leave it to Maxym now.
Thank you for the introduction.
Thank you. Go ahead, Maxym.
So I was working on a project of integrating ML machine learning algorithms for LHC data compression into the ESCAPE virtual research environment under the mentorship of Katerina Yushkevych. A little bit of background. On this picture, you can see the Large Hadron Collider, the LHC, which is located at physics laboratory CERN in Switzerland. The LHC produces proton-proton collisions, and the particles we receive from these collisions are then analyzed by detectors like ATLAS, CMS, ALICE, and from them lots of data is received, and which is open source. And in this project, we'll be using the data from the CMS experiment. The problems we are trying to solve with this project are, first of all, problem that there's too much data produced by LHC experiments. To solve this problem, we can use machine learning algorithms, which will compress the data and improve the efficiency of the experiments. And the second problem is reproducibility. Our goal is to store all the results of the experiments and projects under one platform, the virtual research environment, so that all the researchers could then easily find the data and recreate the experiments. As I said before, we are compressing the open data from the CMS experiment. In the data set, we were using there were 28 variables that describe all the properties of particles received from the experiment. Before compressing the data, we need to pre-process and normalize it. And one of the algorithms we have been using for compression are autoencoders. There are lots of different kinds of autoencoders, but the most basic one consists of 3 components: the encoder, the code, and the decoder. The code is also called bottleneck because of the shape. The encoder compresses the data and produces the code, and the decoder can then reconstruct the input only using this code. Both the encoder and decoder are fully connected neural networks. Code is a single layer of a neural network with a number of nodes of our choice. So firstly, we pre-process the data. While pre-processing it, we remove certain variables that have only 0 values, which will lead us to 24-dimensional data, or 19-dimensional data if we also remove the variables that consists mostly from zeros. The next part is normalization. For it, we first filter out the particles with too high or too low energy, which are considered noise, and also applying the min-max normalization to the rest of the data. On the plots, we can see that we receive the data transformed to the range from 0 to 1. And for the evaluation of the received results, to see how good machine learning algorithms work, residuals were used, the difference between the input data and the reconstructed data, and also the relative residuals or responses. And finally, the final step is data compression. We're taking the implementation of autoencoders from George Delektekis' research. And also in this project, PCA was implemented, another machine learning algorithm, and compared to the autoencoders. We have chosen only the best performing autoencoder, the sparse autoencoder. And the second goal of the project was the creation of a standalone documented Jupyter notebook and uploading it on the virtual research environment. First, the PCA autoencoders comparison. On these plots, you can see the responses of masses of particles. For the 24-dimensional data, the sparse autoencoder is showing himself better than PCA. We can see that on the mean and RMSE numbers. However, what is interesting with residuals, here we have the 8 residuals. PCA is showing himself better. We don't know why is that yet, but that can be studied in the further researches. And as for the 19-dimensional data, the PCA has shown itself better, both for responses and residuals. However, this can be because we've been only training the autoencoders for 50 epochs. So the students that will take on this project after me will try to train the autoencoder for longer. And we'll also use the GPU distribution, since it already takes a long time to train the algorithm, about half an hour of real time for 50 epochs. And if we say want to train it for 500 epochs, it will take us about 5 hours. As you can see from the loss plots and train loss, the train loss and the validation loss lines are gradually descending, and even after 50 epochs. And if we and that means that if we train the autoencoder for longer, we still may see better results. Also, more work can be done to understand more the performance of PCA and autoencoder, and understand why the PCA is showing itself better on the residuals. For that, we can fit the response with a Gaussian distribution. And as for the second part of the project, all the files, the notebook, the open data were uploaded on Ruscio data management service, which is accessible to everyone in the virtual research environment. Its goal is to gather all the different projects from all the different fields which work on solving the same problems. And it's very handy and useful because if someone wants to recreate the results of this project, for example, as the researchers who want to do that, they don't have to go look for the open data which was used in this project and download it manually. They can just log into Ruscio and recreate the same results I had while working on this project. So for the conclusion, in this project, PCA was implemented and compared to autoencoders. As a result, autoencoders show themselves better on 24-dimensional data, and PCA on 19-dimensional data, and also the residuals in both cases, but this is just for now. And also a standalone documented Jupyter notebook was created and uploaded on the virtual research environment so that the results of the project can now be easily reproduced by other researchers. So that's all, and thank you for attention.
Thank you, Maxim. Any questions for Maxim? Okay, I guess I'll ask my standard question. What was the most interesting thing you learned this summer in your project?
The most interesting thing was that I got to know that there are lots of institutions and foundations like IRIS-HEP, like EOS, European Open Science Cloud, and CERN, and that ultimately they have different goals, but they are working on some projects together, and when they do, they get along quite well. So yes, I got to know that world of researchers and scientists, and it was very cool.
All right, good. All right, any other questions? Okay, thank you all. Thank you all for the talks. Thank you for people for attending. We'll have another round upcoming next week. So thanks. Bye.